All right, so we're gonna move on to the second component of a Diels-Alder reaction. Okay, the dienes. Now, the dienes in a Diels-Alder reaction must be in an S-cis conformation. To remind you real quick, so we talk about is in a conjugated diene, that a conjugated diene can exist into two conformations. We have S-trans, right? And there's an S-cis, and S-trans is more stable, okay? Which is a kind of bad news for Diels-Alder reaction, because a Diels-Alder reaction want to form a six-membered ring, and the six-membered ring, it has to look, the four carbon has to look like that, right? Not like that, which means that the S-trans has to be converted to S-cis first by rotating that carbon-carbon bond. Okay, break a conjugation and then rotate to S-cis and then reform the conjugation, but it got still torsional strain, but it's okay. Only 2% actually do the reaction. Okay, so that's why the reaction rate is kind of low. You have to heat up the reaction. Anyway, so, and that's how you form the do Diels-Alder reaction. Some dienes that are locked in an S-trans conformation, like this is S-trans, cannot do Diels-Alder reaction. Right? We want a six-membered ring like that, so that it has to go to S-trans conformation, can do S-cis. Also, it has to be an S-cis conformation, cannot do from the S-trans. Okay, so the following dienes cannot do a Diels-Alder reaction because it's locked. You can't rotate this bond. Is it in the ring? Can't rotate it. For those dienes that are locked in an S-cis conformation, for example, a cyclopentadiene, this guy is really reactive toward Diels-Alder reaction. Okay, so reaction go quick because more all compounds are locked in 100% are locked in an S-cis conformation. Regular dienes 98% in solution in S-trans, so only 2% react. And over time, S-trans have to convert to S-cis. I mean, just concentration is low, right? But as for cyclopentadiene, 100% in S-cis, this guy react quick. Okay, there's cyclopentadiene is that part right there. All right, so the following dienes react quickly with the when you do the Diels-Alder reaction. Okay, very reactive. Now the cyclopentadiene right here is so reactive toward Diels-Alder reaction that it can react with itself. So if you have a solution of on a solution like so it's liquid, right? You leave at room temperature, they react with each other from so they do dimerization, and the product is favored too. Look at this, a thermodynamic product, KEQ 10 to the 6th, right? 10 million favor the product, the Diels-Alder reaction. Okay, and so it says, so I'm going to read right here, the dimer can be detected in a few hours at room temperature, and most cyclopentadiene becomes dimers in a week or two. So think about this. If you have let's say a container of cyclopentadiene, leave it at room temperature, ready to do reaction, a week later all of them just turn to be a dimer. We can't do anything with it. So basically in the storage standpoint, we have to keep the cyclopentadiene at a cold temperature, usually put in the fridge or something, okay, or freezer. And before use, well, we have to perform distillation. Okay, the boiling point of the dimer right here, the Diels-Alder product, is 170 degrees. So we heat up, set up the distillation, heat up to right below 170 degrees. Okay, and if you remember, if you heat up the reaction, so the Diels-Alder reaction favor the formation of the static material. So it breaks down the retro Diels-Alder, and it gives you this monomer of cyclopentadiene left. Okay, so the boiling point of the cyclopentadiene is at 42, so we can collect the compound at 42 degrees. Right, so basically the distillation, this is a simple distillation. So you put the liquid cyclopentadiene right here. Some of them have already become dimer, and heat it up, right? Heat it up right below 170 degrees. So the dimer stay right here, but the diene, the monomer, will vaporize and then condense, and we collect it right there, basically. All right, so just concept test real quick. So just make sure you understand what we talked about earlier. Now rank the reactivity of these. We have 3 dienes. Which one the fastest toward Diels-Alder reaction? Which one the slowest one? All right. If you look at the conformation of the dienes in A, this guy is locked in an S trans. Well, can do Diels-Alder reaction, right? B, diene, but this guy is locked in an S cis or loves to do Diels-Alder reaction. 100% stay at this form. C, a diene, right? This is S trans, but can be converted by a rotate that carbon-carbon bond to be an S cis. Most of C gonna stay in S trans, so some of them gonna stay in S cis. We can also do Diels-Alder, but probably slower because the concentration of starting material is lower, okay, than B. So the reactivity toward Diels-Alder reaction is gonna go B, C, and A, like that. Okay. All right, now if you remember the frontier orbital theory, HOMO LUMO, we're gonna use that and explain Diels-Alder reaction. Okay.